All right. All right, greeting scholars, greeting YouTube. Let's see. So welcome. We are at the top of week 10, right? Basically what that means is that, hang on a second. During week 12, we can anticipate exam 3 over chapter 2. So today we're just continuing. Let's go like this to view. So today we're just continuing our exploration of chapter 2 on polynomials and rational functions with section 2.2 polynomial functions. As always, I'll check attendance again around the 15-minute mark for people that are coming late. And this is remote asynchronous. And if you have questions or comments or concerns, the best way to get my attention is to unmute yourself and just speak to get my attention, or you can type in the chat. I do check the chat periodically. So with section 2.2 polynomial functions, a few objectives are that 1, we like to learn properties of the graphs of polynomial functions. 2, determine the end behavior of polynomial functions. 3, find the zeros of a polynomial function by factoring. 4, we like to identify the relationship between degrees, real zeros, and turning points. And 5, we like to graph polynomial functions. Okay. So this section, we have it's a lot of like terms and concepts and definitions. So we just have to do the best that we can, and we'll kind of navigate that way. So we have this definition. A polynomial function of degree n is a function of this form, right? Where n is a non-negative integer and the coefficients a sub n minus 1, up to a sub 2, a1, and a naught are real numbers where a sub n is not equal to 0, right? So this is a polynomial function where a polynomial, all it is a finite sum of monomials, right? So then, the next logical question is, well, what's a monomial? A monomial is a term where we have some real coefficient times some variable x to some non-negative integer exponent, right? So again, this is some real number times a variable x to a non-negative integer exponent. So then once you identify a monomial, a polynomial is just a finite sum of monomials, all right? And I feel like once you start working a few examples, you'll be able to recognize a polynomial. Okay. Again, where the leading coefficient is not 0. So the term a sub n x to the n is called our leading term. The number a sub n is called the leading coefficient. A naught or a sub 0 is called the constant term. A constant function f of x equals a, where a is not equal to 0. They may be written in the form f of x equals a times x to the power of 0. We say this is a polynomial of degree 0, right? So when you have a function equal to just some number not equal to 0, it can be written in the form f of x equals a times x to the power of 0. Again, that's a polynomial of degree 0. The degree of a polynomial is the highest exponent on our variable, or the highest power on any variable. That's going to be the degree of the polynomial. So then the 0 function, f of x equals 0, we say that it has no degree assigned to it. That's because the 0 function can be written in an infinite number of ways. This is the same as 0 times x squared, but that's the same as 0 times x to the 14. But then that's the same as 0 times x to the 5th, so on and so on and so on, right? All of those collapse to 0. So because there's no unique way to write this function, we say that f of x equals 0 has no degree. So polynomials of degree 3, 4, and 5 are called cubic, quartic, and quintic respectively. So cubic is a degree 3, quartic is a degree 4, quintic is a degree 5. Okay. So then the expression, this guy, finite sum of monomials, we call that a polynomial. Then the function f defined by f of x equal to that polynomial, we say that that's a polynomial function. And then the equation where we have that polynomial equal to 0, we say that's a polynomial equation. right? So 3 different ways that we'll kind of like come across polynomials for our discussion. All right. So then we have some common properties of polynomial functions. The domain of a polynomial function is a set of all reals, right? So that's one property. Again, the domain of a polynomial is a set of all reals. So then when we're considering the graph of a polynomial, it's going to be a continuous curve, right? So like if we look at the image on the left, we can start at any point on the curve and we can get to any other point without having to pick our pin up, right? There are no holes or gaps or breaks. So that's what we mean by the curve is continuous, no holes or gaps or breaks. But if we look at the example on the right, we have this gap here, right? So for instance, if I wanted to start here and if I'm trying to get to something on the far right, then I had to pick the pin up and jump over that gap to continue tracing. So again, because we have this hole or gap or break, then this cannot be the graph of a polynomial function. Okay. So not only are the graphs continuous, but they're also smooth. And what that means is basically that there are no sharp corners, no edges, nothing like that. So a polynomial graph, again, all the curves are smooth curves. If you have a sharp corner, then it can't be the graph of a polynomial. Okay. So then here we're asked to say which functions are polynomial functions. For each polynomial function, find the degree, the leading term, and the leading coefficient. If you had to guess, would you guess that A is a polynomial, yes or no? If you had to guess. Is A a polynomial, yes or no? What do you think?
Yes.
Right? Yes, right? Because, this is a monomial, right? It's some real number times x to some non-negative integer exponent. Same thing here and same thing here. So we have a finite sum of monomials. So then this is a polynomial, all right? So then for each polynomial, the degree, can somebody tell me what's the degree of this polynomial? 4, right? The degree is going to be the power of the highest power on any variable, right? What's the leading term?
5.
A little bit more. So 5, here, let's do this. What's the leading coefficient?
Five x to the 4th.
Oh, okay. I was trying to get you to just repeat what you said. So you got them backwards, right? The leading term is the term with the highest power, which is this guy, 5x to the 4. And then the leading coefficient is the number on the number in the front of the leading term, right? Sometimes these terms are out of order. So when we work on our polynomials, it is a good idea to put it in descending power order. Okay. All right. So if we're looking at B, what's the time? If we're looking at B, if you had to guess, would you guess that this is or is not a polynomial?
It is.
Okay. So one property that we said about polynomials, can you remember, what did we say about the domain of a polynomial? So I think a moment ago we said the domain of a polynomial is all reals. What's this domain here? So this domain is restricted from 1 to 5, right? So because the domain is not all reals, that's the only reason that's not a polynomial. If this thing were not there, then I would agree. I would say yes, it is a polynomial. But because of this restriction on the domain, then it can't be the graph. Okay, that was good. So here's a typed up version of what we just discussed. Okay. So then we have this concept called the power function, right? So that's going to be a function of the form where we have f of x basically equals a monomial. This is called a power function of degree n, where a is a non-zero real number and n is a positive integer. Right, so we have f of x equal to a monomial. Okay, we call that a power function. So then if we consider f of x equal to, if we consider the power function here, and suppose that the n is even, right? So then if we were to consider negative x to the power of n, if we have an even number of negatives multiplied together, we're going to get essentially a positive, right? So then basically we're showing that when we consider f of negative x, we're able to finish with f of x because n is even. So then that's the definition of a function being even. Remember that? F of negative x equals f of x. That's the definition of a function being even. So once we identify the function as being even, that means the graph is symmetric with respect to the y-axis. We have y-axis symmetry, right? So if you were to fold on the y-axis, the left-hand side is going to be a mirror image of the right. And when we're working with the power function where n is even, that graph is going to be similar to the graph of y equals x squared. So y equals x squared is like a U-shaped curve. Our power functions that have an even degree, the graphs are going to be similar to the parabola. Okay, I'll check attendance in just under 3 minutes. So then we looked at the power functions of even degree. Now we want to look at power functions of odd degree. So we want to consider this power function, and then if n is odd, right, and we consider negative x to the power of n, if we multiply an odd number of negatives together, we finish with a negative result, right, essentially. So then if we consider f of negative x, that gives us negative times the original, right? That's the definition of a function being odd. One more time. If we consider f of negative x and we finish with negative times f of x, or negative times the original, that's the definition of a function being odd. Once we identify a function as odd, that means we have symmetry with respect to the origin, right? So origin symmetry is like whenever you have x comma y, you also have negative x comma negative y. All the points are equidistant and mirror images centered around the origin, all right? Okay. And so the graph of a power function where n is odd is going to be similar to the graph of y equals x cubed. So x cubed almost is like an S shape. It's going to go up to the right and down to the left, right? So then our power functions with odd degree are going to behave in a similar fashion to this, okay? Let me see the time. So we still got like almost a minute and a half. Okay, so that should lead us to, we have these 4 cases. So now we want to consider the end behavior of polynomial functions. We're still kind of talking about the power function. And this case is missing something. This is considering when our n is even. Okay, we're considering when n is even. Okay. So the way I usually go about this, first I look at my leading coefficient. If my leading coefficient is positive, that tells me that my graph is going to rise as we go to the right. And so as x goes off to positive infinity, our graph is going to go up. But then if n is even, that tells me that the other side does the exact same thing, right? So the leading coefficient tells me about the right-hand side. The degree of the polynomial tells me what the other side is doing. If we have a positive leading coefficient, our graph goes up to the right. If the degree of our polynomial is even, the other side does the exact same. Okay. So then if we looked at when the leading coefficient is positive, we can also consider when the leading coefficient is negative. We're still working in the case where n is even. So if our leading coefficient is negative, that means our graph falls to the right. If n is even, that means the other side does the exact same. Okay. We saw the 2 cases where the degree of our polynomial is even. Next, we want to consider where the degree of our polynomial is odd. Okay. Let me check. He must have got knocked off. Student. Yeah, that looks right. All right, welcome back. Okay, still missing two gentlemen, but that's okay. And let's keep going. I'm going to share the screen. Okay. So we saw two cases where n was even. So this third case is the first one where n is odd. So again, we just said that when the leading coefficient is positive, our graph goes up to the right. But when the degree of our polynomial is odd, that means the other side does the opposite. So if we're going up to the right, that means we're going to go down to the left. Okay. And then the final case, the leading coefficient is negative and the degree of our polynomial is odd. So if our leading coefficient is negative, our graph falls to the right. If the degree of our polynomial is odd, that means the other side does the opposite. So we go up to the left, right? Okay. All right. Keep going. All right, so given this polynomial function of degree 3, we want to show that this polynomial is approximately equal to 2x cubed when the absolute value of x is very large. Okay, so not that you would be necessarily like working problems in this manner. This is just to kind of provide some context for one concept to the next, right? So if we start with our given polynomial, which is 2x cubed plus 5x squared minus 7x plus 11, okay? And let's factor out x cubed from all the terms. So if we factor out x cubed, we're going to be left with 2 plus 5 over x minus 7 over x squared plus 11 over x cubed. Okay? All right. So now what we want to do is let the absolute value of x get very large. Let it run to infinity. Okay. So as x goes off to the far right, or the absolute value of x goes off to the far right, then the terms this 5 over x, this negative 7 over x squared, and this 11 over x cubed, right? Riddle me this. So if the numerator stays fixed and the denominator of this fraction keeps getting bigger and bigger and bigger, is this fraction getting bigger or is it getting smaller? Let me say that one more time. If the numerator stays fixed and we let the denominator get bigger and bigger and bigger and bigger and bigger, as that denominator is bigger, is this fraction getting bigger or is this fraction getting smaller? Let's play with some numbers, right? For instance, if x were 1, what's this answer? What's 5 divided by 1?
5.
5, right? Say x is 10. What's 5 divided by 10?
2.
Almost. 5 over 10. What does that reduce down to?
1.5 or 0.5 rather, sorry.
1 over
0.5, 1.5.
Yeah, 0.5 or 1/2, right? So when x was 1, it was 5. When x was 10, we got a half. What about if we said if x were 100? What should that result be? 1 over, what is it? I think we went from a half to, I think it's going to be 20, right? What if we did 5 divided by 1,000? 1 over, can you give me that number?
200.
200, right? So notice that as that denominator is getting bigger and bigger and bigger, our output, is our output getting bigger or is our output getting smaller? Right? Which is bigger? If we did 5/1 equal to 5, which is bigger, 5 or 1/200? Okay, here, let's do this one. 5/1 equal to 5 or 5/10 equal to a half? Which is bigger, 5 or a half? Okay. I know you know it's a half. Like, I don't know why you're afraid to say it. Like, I know you know. I just need you to not be afraid. So, long story short, as that denominator gets bigger and bigger and bigger, those fractions are getting smaller and smaller and smaller. So as the absolute value of x runs to infinity, this guy tends to get smaller and smaller and smaller, gets closer and closer to 0. Same thing here. This gets closer and closer to 0. This gets closer and closer to 0. Again, we have some fixed number divided by a really, really big number. So when you have a small number over a massively large number, then that's essentially that's a really, really small fraction. So it's really close to 0. So as the absolute value of x goes off to infinity, those terms tend to 0. So then what we get is, and again, this is just providing context. You don't have to like do all of this. This is just to kind of prime the next concept. So then what we're getting is that our original polynomial is going to be approximately equal to x cubed times 2 plus 0 plus 0 plus 0, which is approximately 2x cubed, right? That's what we wanted to show, was that the original polynomial was approximately equal to the power function. So, and we just went over those 4 cases with the power function. We saw 2 cases when the degree of our polynomial is even, and what happens? We saw 2 cases where the degree of our polynomial was odd, and what happens, right? So we had those 4 cases for the power function. We can extend those 4 cases to a general polynomial, right? So they kind of do it. It's kind of like a direct correlation or translation or whatever. So let's look at it. So then that brings us to this leading term test. Leading term test. Now let's see. So if we consider the polynomial function, right, where the leading coefficient is not 0, the leading term is an x to the n, then the behavior of this polynomial function as x goes to plus or minus infinity is going to be similar to one of the following 4 graphs, and is described as shown in each case. The middle portion of each graph indicated by dashed lines is not determined by this test, right? So this leading term test is going to be similar to the in-graph behavior that we saw a moment ago for the power function. You see, here's the first case here. Let me see, can I paste? That's fine, I guess. Let's get rid of this and this. Again, here, we're considering our n is even. Let's go like this. Our n is even. Okay, let's get a copy of this. Okay. Right. So, and it's very similar to what we discussed a moment ago. Notice a positive leading coefficient means our graph goes up to the right. If the degree of our polynomial is even, that means the other side does the exact same. We have no idea. This doesn't tell us anything about what happens in the middle, but it just tells us what happens as x goes to positive infinity or negative infinity. Okay. Let me make sure I got a copy of this one more time. Let's copy. And then this is, again, where n is even. So now we have a negative leading coefficient. So that means our graph is going to fall to the right. And if n is even, that means the other side does the exact same. Right? Okay. Okay. So the case number 3, instead of n being even, now our n is odd. Okay. Again, similar to before, when our leading coefficient is positive, that means it goes up to the right. When n is odd, that means the other side does the opposite. Okay. And then the final case is where the leading coefficient is negative, and we're still working with n is odd. So the leading coefficient is negative, means the right-hand side goes down. With n being odd, the other side does the opposite. So for me, the way I remember that, even means the other side does the exact same. Odd means the other side does the opposite. Okay. All right. So that's the leading term test, which is an extension of the long-term behavior of the power function, right? They're kind of the same thing, just for two different types of functions. So then use the leading term test to determine the end behavior of this graph, right? So the leading term test, we need two pieces of information. We need the leading coefficient, we need the sign of the leading coefficient, and we need the degree of the polynomial. The sign of the leading coefficient and the degree of the polynomial. Okay. Let's see. Can someone tell me the sign of the leading coefficient? All right. So the leading coefficient is going to be the number in front of the term with the highest degree. So what's the leading coefficient? Nobody?
-2.
-2. There it is. So then our leading coefficient is -2, which is negative, right? And can you tell me the degree of this polynomial? Okay. So then degree is 3, which is odd. Okay. So then with a negative leading coefficient, that tells us our graph is going to fall to the right. With the degree of the polynomial being odd, that means the left-hand side does the opposite. So that means it's going to go up to the left. We don't have any information about the middle just yet, but we know the graph should fall to the right and rise to the left. Okay. And you can see a typed version of the explanation here. So here in the degree is odd and the leading coefficient is negative. So that means we're working with case 4. Oh, and these are typos. I need to fix these. So I've been doing these as red. Those little R's are just didn't process the image properly. So then I'm just gonna go like this. Copy. Paste the image. This guy. Delete. Copy. And so all those R's are supposed to be arrows. They just, like I said, this just didn't process properly. So I'm gonna do a shameless movie plug for Jamie Foxx. I watched, I don't know, I've gotten better about like just watching random stuff on like Netflix because I used to, I don't know, but I ended up watching his movie called Day Shift. That was like way better than I thought it was gonna be. I had low to no expectations for it, and I don't really want to hype it up too much, but I enjoyed it. It was, as long as you don't mind a little bit of gore, but the action scenes were actually pretty good, and it was entertaining. I don't know, just a shameless plug. I don't know, just something random. Okay, let me see what's the time. Okay, let me check Zoom really quickly. Okay, looking good. I gotta check on these other students. I know I haven't seen these guys in a minute, and so I gotta follow up, see if they're okay. So yeah, those R's were typos. They're supposed to be arrows. Okay, And this was just a type version of what we just experienced. So, okay, I'm gonna let that be for now. Let's see. So then we have the real zeros of a polynomial function. If f is a polynomial function and c is a real number, then the following statements are equivalent. So if we were to say c is a zero of f, or we said c is the solution or root of the equation f of x equals 0, or we said c is an x-intercept of the graph of f, these three statements are synonymous. They mean the same thing, right? So if we ever use one implies the other two. Okay. Okay. So here we're asked to find all the zeros of each polynomial function. Okay, so this is factoring, right? So I know that we have a lab. So, you know, for our class, the main things are that we make sure that we're just completing our assignments on Pearson and that we are following the instructions of Dr. Lamar, the facilitator for the lab. Those are the main two components for this class, right? And just to get those things in there. Find out the zeros of each polynomial function. Okay, so like, do I need space? Let me give myself some space. Come on. I think 1 is enough. And let me change this view to seamless. Okay. So let me start by getting a copy of A and B. So for A, we have f of x equals x to the 4 minus 2x cubed minus 3x squared. And then for B, we have g of x equals x cubed minus 2x squared plus x minus 2. Okay. I just want to take all of this. I just want it like right here. Okay. So we're asked to find the zeros. So in other words, we want to set each of these to 0 and solve. So for part A, and let me, there used to be a ruler. Let me see if I could find it. It's okay. So I kind of want to try to work in here. Okay. So for part A, if we set it to 0, we're going to have x to the 4 minus 2x cubed minus 3x squared equals 0, right? So then if we're factoring something of this nature, first thing we want to ask ourselves, is there a greatest common factor? And there is. It looks like all the terms. Can somebody identify the GCF? What is it that all three terms have in common here for part A? So they all have x squared, all right? So then if we factor our x squared from the first term, we're left with x squared minus 2x minus 3 equals 0. Then we want to see, can we factor this trinomial? Okay, let me kind of shift things a little bit. That. Okay. So then equals, so we want to see, can we factor this polynomial into a form like this, okay? Where we have x and x. The second sign tells me my two signs are opposite. So I know that one is positive and one is negative. This first sign tells me my larger number is negative. So two numbers that multiply to give me -3 and add to give me -2 are -3 and +1. Okay. So then here we can invoke the zero factor property. When you have two or more things that multiply to give a 0, you basically set each thing to 0 and solve. So that way, if any one of them are 0, everything collapses to 0. So if you set each factor to 0 and solve, you'll get x equals 0, you'll get x equals -1, and x equals 3. Okay. Now we can check this in the original by plugging these in. I think just probably being lazy, I probably am not going to do that right now. But if like this were a testing environment, I would just plug it in. I'm just going to go with it for now. So then for B, We want to do something similar. We want to find the zeros, okay? So let's start by setting it equal to 0. So then we have this x cubed minus 2x squared plus x minus 2 equals 0. Okay, right there. Okay, so I'm going to use this technique called factor by grouping, right? Whenever you have 4 or more terms, you might try grouping them in different fashions until something works, right? So I'm going to group the first 2 terms together and then try factor by grouping. So if I focus on the first 2, can anybody identify the GCF? What do they have in common in those first 2 terms? I think they both have what? X squared?
X squared. Yeah.
Yes, okay, my bad. I should have been a little bit more patient, my bad. But yeah, they both have x squared, right? And so that's going to leave us with, I think, x minus 2. Let me do like this real quick. Both have x minus 2. And then on the right-hand side, we're still left with another x minus 2, okay? So then at this stage, we have this thing plus this thing, right? So what does the left have in common with the right? They both have that blue x minus 2. We can factor out that blue thing for both of them. That's called a common binomial factor. So then if we factor out the blue thing from both of those, x minus 2, we're going to be left with x squared plus 1. Okay. Okay. So that was a demo on factor by grouping. That's one of the techniques that we use when we're trying to factor something with 4 or more terms. If you need more practice or help with factoring, I do have a couple of handouts on Blackboard. I have 2 of them. One of them is a PDF that's a summary of how to approach a factoring problem. It kind of like, first thing is you consider your greatest common factor. Then you ask yourself how many terms, 2, 3, or 4. And then depending on how many terms you're trying to factor, that kind of points you towards some other these different techniques or whatever. But that's a PDF that's on Blackboard right now. And then also in that same location where that PDF is, you'll find a chapter devoted entirely to factoring. So it'll go over pretty much all the factoring scenarios that you'll come across for our discussion. So if you just needed practice on factoring, those are available on Blackboard. It's like scans or copies from a text that I've worked with in the past, right? So to finish this one out, now we invoke the zero factor property. So when we have 2 or more things that multiply to give us 0, if you set each thing to 0 and solve, we'll be done, right? But notice this guy here, if we set this to 0 and solve, if you think about this graph by itself, it's a U-shaped curve that's been moved up by 1, right? So when will it ever touch the x-axis? It won't, because this portion sits entirely above the x-axis. So it's never going to be equal to 0. So this guy, you're not going to find the x that makes it 0. So then it's only going to come from the x minus 2 in this case. So then we're just going to say x minus 2 equals 0, and then so x equals 2. So 2 is the only solution here. Okay. Let me see what's next. My favorite time of the day. It's quitting time. Actually, my favorite time of the day is sunrise. I'm usually up at sunrise. Like I just be up. But again, yeah, we would normally check those in the context of the original. I'm just going to piggyback off of. I'm going to piggyback off of my type notes just for the sake of time. All right, let's go like this. So for part A, I think you can see those 3 results that we got: 0, -1, and 3. And then for part B, the only 0 is going to be 2, since x squared plus 1 is always greater than 0 for all real numbers x. In other words, you won't be able to get that to be 0. Okay. Let me see. Okay. We do need to talk about this. Let me take some time to go through this concept. I don't want to keep you more than 4 minutes though. So let A and B be 2 numbers such that A is strictly less than B. if f is a polynomial function such that f of a and f of b have opposite signs, then there's at least one c between a and b for which f of c equals 0, right? So the intermediate variant theorem, if we're working with a polynomial function and we have some a is strictly less than some b, and then if you have f of a has a different sign than f of b, then there has to be some c here between b and a. Basically, the graph has to cross the x-axis. So there has to be a c between b and a such that f of c equals 0, right? So again, as long as you get that sign change, you're working with polynomial functions, because this is an extension of the property that because the graph of a polynomial is continuous, which means it's a smooth, unbroken curve, and if you have a sign change, then it has to cross the x-axis, which means you have to have a 0 or an x-intercept somewhere in that interval, right? And this is like if your f of a was negative and your f of b was positive, to go from negative to positive, you have to cross the x-axis. So there has to be an x-intercept or a 0 between a and b. Okay. So that's the intermediate variant theorem. And then this is an extension of it where you could have multiple points that cross the x-axis between your a and b. So you're not limited to it being exactly 1. It could be, it's basically saying there's at least 1 0 with those given conditions. Okay. All right, this will be it here. So in order to show that this polynomial has a real 0 between 1 and 2, we're going to evaluate when x is 1, you get a result. We're going to evaluate when x is 2 and get a result. As long as they have opposite signs, then there has to be a 0 or an x-intercept between x equals 1 and x equals 2, right? So when x is 1, 2 times 1 cubed plus 4 times 1 plus 5, negative 2 plus 4 plus 5 is 7. It's positive. Okay. So then when x is 2, negative 2 times 2 cubed plus 4 times 2 plus 5, negative 16 plus 8 plus 5, 13. So I think that one is negative 3. So that one is negative. So we got our change in sign and we're working with a polynomial. So that means that somewhere between x equals 1 and x equals 2, it has to cross the x-axis. So there has to be a 0 between x equals 1 and x equals 2. Okay. That was a demo on the intermediate value theorem. Are there any questions? I feel like there should be questions, but you might need some time to think about this stuff and practice it. Let me go ahead and make a copy of this available. It is 4:44 in an auspicious time. We're going to send it to box. I think that's right. Let's send it there. So when this bar finishes loading, you'll get a copy of anything that you saw me writing. If there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, guys, take care. Peace.